Welcome, everyone. I am so incredibly pumped to have you here for this explainer. Today, we're going on a seriously mind-bending spatial journey. We spend so much time fixated on the familiar planets right here in our own neighborhood. But today, we are looking way past them. We're zooming all the way out to explore the completely fascinating, dynamic, and surprisingly complex stuff that exists entirely outside of our solar system. Okay, let's dive right into this. Because to really get a handle on what lies beyond our solar system, we first need to shatter a massive misconception. When we look up at the night sky, it is so easy to just assume that outer space is a perfect, totally empty vacuum, like literally nothing out there, between the celestial bodies. But as it turns out, that's completely false. Space is far from empty. See, even right here inside our solar system, we have what's called the interplanetary medium. It's filled with localized plasma, solar winds, but it holds a super low density of only about 5 particles per cubic centimeter. But the second we push past the protective magnetic bubble of our solar system, we enter the interstellar medium. And as we're going to see, this huge interstellar void is actually packed with a surprisingly dynamic mix of cosmic dust, gas, and rays that are just waiting to be explored. Let's move to our roadmap and see how this all builds. We're going to zoom out step by step, starting at the solar system's edge, moving into our local interstellar cloud, then the broader interstellar medium, cosmic dust and rays, and finally wrapping up with the galactic habitable zone. All right, part 1, the solar system's edge. So where exactly does home end? Before we step out into the great unknown, we've got to anchor ourselves at the boundary. The true cosmographic edge of our solar system is a region known as the Oort cloud. This is a theorized massive spherical cloud made up of billions, honestly, possibly trillions of icy planetesimals. We are talking about giant chunks of ice, water, methane, and carbon monoxide. And these objects are only weakly bound to the sun's gravity, making this the absolute final frontier before galactic gravitational forces fully take over. To really grasp the unbelievable scale of this boundary, we measure it in astronomical units, or AU, with 1 AU just being the distance from the Earth to the Sun. Get this, the Oort cloud stretches from roughly 2,000 to an astounding 200,000 AU away. To put that into perspective, it means the very edge of our solar system sits roughly 0.03 to 3.2 light years away from our Sun. It is just a massive, awe-inspiring icy shell. Moving right along into part 2, our local interstellar cloud, also known as the local fluff. So what exactly happens when we step completely out of the Oort cloud? Well, we enter the immediate galactic neighborhood that our solar system is currently traveling through. Astronomers affectionately call it the local fluff, though officially it's the local interstellar cloud. This thing is roughly 30 light years across. Now, what's really wild about this is it has a temperature of about 7,000 Kelvin, which is literally as hot as the surface of our own sun. But fun fact, if you floated out there, you'd actually freeze rather than burn up. Why? Because the material itself is just incredibly sparse. Just look at the numbers here. If you go to the very edge of Earth's atmosphere, say about 100 kilometers up, you're still going to find about 12 trillion molecules per cubic centimeter. But out in the local interstellar cloud, there are only 0.3 atoms per cubic centimeter. It's almost nothing. Its specific heat capacity is virtually zero, simply because it is mind-bogglingly empty compared to anything we'd ever experienced down here on Earth. All right, section 3, the interstellar medium. Let's look at the space between the stars. As we zoom out even further into the broader interstellar medium, we see a really stark divide in its makeup. It's about 99% gas and just 1% dust. But hey, don't let that 1% fool you. That tiny, tiny fraction of cosmic dust contains absolutely crucial elements like iron, silicates, carbon, and dirty ice. It is literally the fundamental building block for future planets and stars. And if we look at that vast 99% gas portion, it's actually chemically pretty simple. It is overwhelmingly composed of roughly 90% hydrogen and 10% helium, with only the absolute faintest traces of heavier elements. But here's the real challenge for us. This gas can be incredibly cold, sometimes dropping all the way down to temperatures of just 10 Kelvin. And this brilliantly illustrates our next problem. Because this gas is so insanely cold, it doesn't emit visible light, which makes it completely dark to standard optical telescopes. So, to get around this, astronomers have to rely on longer wavelengths along the electromagnetic spectrum. specifically infrared and radio waves, just to directly observe these freezing cold, invisible pockets of gas. But when astronomers do utilize those specific infrared and radio wavelengths, wow, the dark, empty sky suddenly comes totally alive. Telescopes reveal these breathtaking, sweeping, dusty nebulas that are completely hidden from our naked eyes. Thanks to this tech, we can finally see the dense clouds of gas and dust where brand new stars are actively being born. Which brings us to Section 4, Cosmic Dust and Rays, the particles in motion. Now that we can actually see this medium, let's look at what's moving through it. I absolutely love this quote from the researchers who are mapping interstellar space. The specific composition of this space dust, how much of each element it contains, is a postmark for where it comes from in the galaxy. Isn't that a great analogy? By studying the exact chemical makeup of dust grains, scientists can trace the galactic origins of these cosmic materials. It gives us this incredible insight into stars sitting way, way outside our solar system. But, it's not just dust floating out there. There are also these highly energetic cosmic rays. So where do they come from? Well, research shows they're accelerated on propagating shock waves, very often inside that partially ionized interstellar gas we talked about. And what's truly fascinating is the timing. Scientists actually figured this out by looking at specific isotopic ratios. Think of them basically like radioactive countdown clocks. These ratios prove that these cosmic rays are actually launched into space no less than 100,000 years after the initial supernova explosion takes place. Just mind-blowing. Finally, Section 5, the galactic habitable zone. Let's talk about where life can actually survive. For our final act here, let's zoom out to the macro level of the entire Milky Way galaxy. Because just because a planet is in a solar system doesn't mean it's safe. The galaxy itself has its own habitable zone dictated by 3 massive constraints. First, the inner disk of our galaxy historically faced a supernova threat 20 times greater than what Earth experienced, which would just routinely sterilize planets. Second, the galactic bulge has a really high stellar density, and that creates this pervasive, intense radiation field. And third, you need enough heavy metals, or metallicity, to actually form rocky terrestrial planets in the first place. So, the crucial point is, when you eliminate that inner bulge because of all the radiation, and then you eliminate the galaxy's diffuse halo and thick disk because they lack the necessary metals to build rocky planets, what are you left with? You are left with the Milky Way's thin disk. This is the hospitable middle ground. It's basically the ideal cosmic real estate where our solar system comfortably resides, totally protected from the extremes of the wider galactic environment. And that brings us to the end of our cosmic zoom out. We have traveled from the icy boundaries of the Oort cloud through the sparse local fluff into the massive clouds of interstellar dust and all the way out into the habitable rings of the Milky Way. Knowing that every tiny speck of dust acts as a chemical postmark from a distant star, it really leaves us with one provocative thought. What other elemental fingerprints are floating silently through that invisible void, just waiting to be discovered by our telescopes? Thank you so much for joining me on this explainer, and keep your eyes on the stars.